Thank you everyone for joining. This is the introduction and training session for Storlytics v4, which we just released last week. We have a number of very critical and much requested updates that we have implemented in this version, and we're really excited to share them with you and train everyone on how to use them and really kind of leverage the new features we've installed. So for the agenda, we'll start with reviewing the agenda here and the timings of different items. From there, we'll go to some quick housekeeping and attendee PC preparation. After that, at 9:15, we'll start with our first case study, which will be on BESS project financial evaluation. So the focus there will be on really showing how one can quickly and simply review financials of a BESS project in a relatively short period of time. Then we'll switch to hands-on training on how to maximize BESS project IRR. From there, we'll have a 10-minute break. That's going to be at 11 a.m. Eastern Time. After the break, we'll come back and do a training on designing BESSs for data center applications. And after that, we'll switch to a training on designing BESSs for solar plus storage applications. And that will be followed by Q&A session. So to get things started, we wanted to just introduce ourselves and our company here. So Storlytics is a software company focused on grid-tied battery systems. What sets us apart is that we focus very heavily on the accuracy of modeling of battery cells, enclosures, inverters, really all the components that comprise a grid-tied battery system, because we firmly believe that it is crucially important for evaluation of business cases, financial models for these types of systems. In addition to that, our platform allows our users to set a lot of details when it comes to the use case, because that is another very important component that affects how a battery system will perform. So really combining these two main aspects, accurate models for different system components, plus allowing users to be very specific on how a battery system will be dispatched and its location, allows the production of very accurate results when it comes to degradation forecasting, energy loss estimation, auxiliary load, and that in turn results in very accurate financial modeling. So a little bit about Storlytics as a company. We have two main offices. Our headquarters is in Charlotte, North Carolina. We have a regional support office located in Cairo, Egypt. Okay, so switching to some housekeeping notes here. Just keep in mind this session is being recorded. By remaining in the meeting, you consent to this recording. We will share the recording later with attendees so that in case, for those of you who are unable to activate Storlytics in time or ran into issues, you will have the recording, so you should be able to view it later and follow along there. This is intended to be a conversation, so please don't hold back on questions. We'll try to address them as much as possible. There are over 120 registrants, and actually it's now 140 registrants. So we'd really appreciate it if folks use the raise hand feature. Our team members are monitoring and they'll let the presenter know that someone has a question, and then they'll call upon you to ask your question. In this training, we'll be using Storlytics v4, which is a beta version that was released last week. So we may encounter some bugs here and there or typos. Don't worry about that. They should be addressed in the next release. If you haven't already activated Storlytics, feel free to try and do that. If you run into any issues, feel free to message Hidayah or Luay, who's on the call. They'll help you out as much as possible. And finally, throughout this training, we'll be going through some pricing information. This pricing is not specific to any company, they're just for illustrative purposes. All right, presenters here. So this is Sherif Abdelrazek, co-founding CEO of Storlytics. And with me here is Jakir Hossain, co-founding Chief Technology Officer at Storlytics, and we'll be presenting the different training cases in this webinar. For setting up your PC, for those of you who attended our workshop in May, we spent quite a bit of time getting the example files into people's Storlytics user files. That won't be required here with Storlytics v4. The default user files are in the cloud, so if you're already running Storlytics and you have been running it from yesterday or even from this morning, what we'll want you to do is just restart it, simply close it and start it again. That way it'll update the default user files from the cloud to make sure you have all the webinar examples downloaded. You don't need to do anything, just restart Storlytics and you should get a message saying that your default user files have been updated. And if you have any questions about that or running into issues, like I said, reach out to Hidayah, who's on the presentation panel here, and or Luay, who's also there. Go ahead and start here with the first case, or just before that, let's go over the outline here. So we'll cover 4 cases. The first one is going to be about just financial evaluation of a BESS project. Second one, finding the best design to maximize project IRR. So that will include both kind of the cost side of the equation and the revenue side. And then a very common and popular application these days, designing BESSs for data center applications. And from there, we'll take a case about a hybrid solar plus storage application. So for each of these cases, we'll, in the beginning, just to set the stage, we'll describe the scenario as much as possible so that folks are familiar with, not just what we're doing, but why we're doing it. From there, we'll cover how to develop the usage profile or the dispatch profile for the battery system, and then shift to actually designing the battery system for each of these. With the first case here, BESS project evaluation. So what I'll do here is I'll ask people, for those who have Storlytics installed, to open it up at this point. And if you can just give us a thumbs up that you've opened Storlytics and you're ready to go, that'd be great, so we can make sure as many people as possible are following along. Oh, check the chat. Okay, I see some thumbs up there. All right, I think we can probably now start. And like I said, if anyone is facing any issues, just please feel free to reach out to Dea or Luay. Okay, so for this case, I'm going to start from scratch here. So we'll click new. But before we kind of jump there, let me just describe the case there. Case description here. We're being asked to provide an estimated cost for a BESS project that will be controlled by a utility as part of a tolling agreement. And this tolling agreement has the following characteristics. The project capacity needs to be 100 megawatts at the point of interconnect. The energy capacity, 400 megawatt hours at the point of interconnect. The utility said it will be cycling the system at most 1 cycle per day. Project life, 10 years. Location here, for this example, we'll do New York. And deployment strategy, overbuild. So for this specific case, we won't have any augmentations over the 10-year life. Battery chemistry, lithium iron phosphate. Right. So with that, we can kind of jump in here. So first thing we'll do is just input the project name, that's cost valuation. And then next we'll fill out the information needed in the general tab. We don't really need to specify a power and energy requirement, so we can start with the project life. So define that as 10 years. Deployment strategy, we'll keep that as user defined since we won't have any augmentations. Auxiliary load source, we'll select a separate source for this example. That just means auxiliary load will not be fed from the same point of interconnect. And then for interconnection, we'll do a T-tide system. And once you kind of select T-tide, you'll see that a generation step-up transformer appeared in kind of the schematic. We'll then turn on the deduce financial results because the whole point of this example is to evaluate the financial performance of this project. Deduce battery degradation, definitely want to take that into account. So we turn that on and we'll select the initial state of health to be 100%. In a lot of cases, users set this to 99 or 98% to account for maybe state of health impacts that will occur in shipping, but you can do it both ways, really. And finally, we'll click deduce enclosure temperature regulation aux load. And what this does is allows the platform to automatically deduce what is going to be the energy lost and auxiliary load automatically based on where the project is located. Once that is done, we can then kind of switch to the interval data. And under here, we'll switch to standard cycle. And we'll specify the target POI power as 100 megawatts, as we have in the example. In the example, the target energy is 400 megawatt hours. So we'll select the duration of 4 hours here. And for number of cycles per day, we'll select 1 cycle per day because that is the maximum cycling that the utility specified in this tolling agreement. Now from here, we'll also select the typical meteorological year file to be New York to the equipment tab. So under the equipment tab, we can select the battery model here as a generic LFP. For this one, we can do a 306 amp hour cell. And then for the inverter, we can do an SMA inverter, so semi-central storage 3950. And then for the enclosure, we can select an air-cooled. So once you've completed this information, you'll see that the auto size project button has turned on. So then you can click on that. And in V4 here, when you click on auto size, it'll show you kind of a summary of all the settings you have. You can make any changes if you want to in this view. But in our case, we just want to run this case. So it just confirms, that your overbuild basis, your overbuild period, and it just tells you that because degradation is on, this simulation tends to take a little bit of time. And the reason kind of it takes some time is that in the backend, Storlytics is iterating through different designs, because as you cycle a battery system with different sizes, the effective depth of discharge is different, which means the degradation is different in each case. So it has to be kind of an iterative approach. All right, so while that is running, we can kind of open it up here if there are any questions. Right, I see a question. There was a question in the chat about the TMY3 files. Those are available publicly. You can get them on NREL's website. I see Jakir shared a link there. That link has a TMY3 data from different cities in the US. I think there's also some repositories available the rest of the world online. Right. And just while kind of auto size is still running here, what I'll do is I'll just open another instance of Storlytics to kind of walk folks through the step after that. All right, here we go. All right, so in this instance, I'll just load kind of the solution that was put together. All right, so here after auto size completes, if you go to the system specs tab, you'll see that all the data has been filled out. So what has been filled out? The number of modules per rack, number of battery racks per inverter, and then number of inverters for the project. And as these have been filled out, you'll see here the total capacity is now showing next to the DC block, and also the total power capacity is shown next to the inverter.
Hey, Doctor, real quick, there are some questions in the Q&A section. So
Okay.
Spartak is asking, what is the definition of interconnection, T-tide, and...
Okay. Yep. So interconnection T-tide means transmission tide. So when you select T-tide here, you'll see a GSU transformer that steps up voltage from medium voltage here to high voltage here. D-tide is distribution system tide, which implies that you're just connecting to the medium voltage distribution system. So you won't, in that case, have a generation step up transformer.
All right. There's also Sandra asking if we can set the maximum state of charge to be 100%.
That is not permitted. I think you can go up to 98 or actually 97%. Now, the reason that is not allowed is because really physically, you cannot cycle a battery system at 100% because the state of charge that's used in Storlytics is the actual installed state of charge, which means there is a certain portion of it that you just can't get out because of losses within the battery itself. And also once you get to that very high state of charge level in a grid application, you need to switch to constant voltage mode, which is not, grid tied inverters really don't operate in that mode because you need to be able to control the power that is being dispatched from or to your battery. Additionally, on the kind of minimum state of charge for lithium, when you get into that lower state of charge range, you start to approach that exponential range, and then estimating voltage becomes really, really difficult and unreliable. So that's why in reality, OEMs don't allow you to go down to 0% state of charge. And you have to be kind of aware, some OEMs may say 100% depth of discharge, but that's mostly just using a different base. It's just based on dischargeable energy, but not the actual installed energy capacity. So Storlytics use installed energy capacity, which is the energy that could be stored in a battery if it was 100% ideal with no losses. Okay. All right.
There's also Sampath. He's asking on what basis did we select inverter model?
Okay. So let's do this. Let's run, for the benefit of everyone else, let's run through the example till the end, and then we can do kind of Q&A. I just want to be kind of mindful of folks that want to get to the end of it. All right, so here, once auto size is done, and I'll actually kind of go back to the main window I have and close this new one because auto size has completed. So these kind of inputs have been, loaded automatically. Losses has also been filled out automatically. So this is the transformer copper losses filled out with 1%, transformer core losses 0.1%, and here just 0 aux load, just constant aux load. This is, users may want to specify control aux load. This is a good place to put it, but the lion's share of auxiliary load being consumed by the system is going to be your HVAC, and that's being automatically calculated. Operation as well, typical values have been filled out here. So maximum state of charge 95%, minimum state of charge 5%, and initial state of charge 10%. All right, and then under the financial model tab here, you can go here and if you're kind of following along, select the generic lithium LFP underscore ITC. And that's just to make sure that we're accounting for the investment tax credit as we're assuming this project is here in the United States in New York. And then turn on deduce cost. It should be already turned on by default. And then deduce revenue should also be turned on by default. And then we'll just really turn on everything here for, just because we want all the cost components here to be automatically deduced. And then for the revenue, we'll specify here tolling agreement. And then placed in service, we'll assume this project will be placed in service in 2028. And for the contract terms, we'll assume a 10-year contract term because that's what we have there in the example statement. We'll leave the energy capacity LD, RT LD, and availability LD right now as off. And then we can go ahead and click run.
In the meanwhile, Al-Jermain has his hand up.
Sure, go ahead, Al.
Yeah, it was back to the transformer losses. And just simply, that's for the medium transformer, probably.
It's a very good eye, Al, but we've actually in V4, yes, traditionally in V3, this one was for the medium voltage transformer, but in V4, these losses are applied to both the GSU and the medium voltage transformer if the interconnection is T-tied.
I see. Okay, thank you.
Yep. Right. Is there any other question while the simulation is running? Okay, one of the questions here, so typically how you want to select the inverter is based on the sizing of your project. So in this case, we have a 100 megawatt project. So you definitely would not want to pick a 60 or a 50 kilowatt string inverter, right? You want to kind of benefit from economies of scale and have kind of a more central inverter. But if you really wanted to dig into the details, you can kind of open the inverter model, look at the efficiency tables and kind of compare to decide on which product would be best for your project. Simulation has completed here, so we'll click generate report.
Sherif?
Yes, go ahead.
Actually, in our RFS, I have seen that there are 2.5% degradation is allowed. So committed throughput year to year is less. For example, for 10 years or 15 years. But here, if we are planning in our build, and then degradation is means this design is considering that at after 10 years, the throughput will be same 400 MWh, whatever we are planning. But it is not like that in their case. Then how you design this one? For example, after 1 year, we have to reduce throughput. Committed throughput is 2.5% less from the initial year. Or after 3 years, it will be around 7.5% will be less. So how we are considering this one?
Okay. So if I understood your question correctly, you're saying that the depth of discharge would be different as kind of the years progress and as the battery degrades. And you're right, the effective depth of discharge would be different if you're taking into account the new kind of installed energy capacity, which has degraded.
No. Sorry, excuse me. I'm not telling this one. Means the whatever the contractually they are asking that every year you have to deliver not exact what in initial year. Means, for example, after 1 year you have to deliver standard cycle. I'm saying like we are designing right now. You have to deliver at POI 2% less per year every year. For example, like that.
Yep.
That is a
Oh, so that's a different case. Yeah, I'd be more than happy to kind of discuss that case in much more detail. Perhaps we can connect separately, Dr. B. But for this case, let's get through this one and then we can talk about that one later. All right, so back to this one here. So in this case, we're cycling the battery per the tolling agreement. We're assuming the worst case scenario from the utility, which is it is utilizing the full cycling. It is allowed per the tolling agreement, which is 1 cycle per day. So let's now look at the results in the report. So the first thing I'll kind of go to is the degradation results here. So the first thing we'll notice is that the battery installed capacity is quite higher or quite greater than the actual needed capacity for the system. And that's mainly because we auto size the system to last for 10 years, which means by year 10, we wanted to make sure that we had more than 400 megawatt hours dischargeable at the point of interconnect. So here at the battery terminals, we have about 494 megawatt hours, and at the POI, that translates to 415 megawatt hours, which means the project requirement has been met. Right, and then here we can see a plot of the point of interconnect energy capacity as it degrades over the project lifetime. And then from there, we can start looking at the financial results. Right, so here we can see that we're about in net present value cost about 156 or so, $150 million in net present value cost. And so what are the components of that? You have more than 50% of that, about 90 million in DC block cost, PCS cost here in orange, and GSU and high voltage breaker cost, and then balance of plant cost here as well. So if things are not clear in this chart, you can always go back to this table to inspect different components here if need be. And then finally, the state of health guarantee cost. Most integrators will charge you a yearly fee to maintain the state of health guarantee, or other times it's to maintain the use of their power plant controller. So that is kind of here in the gray bar here. And then here finally, cost of energy losses throughout project life. Next is the annual OPEX. So how much are you spending yearly? So everything up here was obviously net present value, but here that's kind of broken out by year. So energy loss has much more detail, and we can also see what we're paying for the state of health guarantee once the warranty kind of runs out. And obviously, these are all parameters that you can kind of edit in the financial model you're using. Here we have some typical values for of course, the financial parameters, but also for the system cost. So equipment, right? You can update that per pricing that you receive. OpEx costs that we were just going over doesn't apply here, but augmentation costs and balance of plant costs as well. And then next here, annual revenue. So since this is a tolling agreement with a specific revenue amount per kW or per megawatt month, it's basically a constant revenue. But obviously, if you select merchant market, it'll be variable based on what the battery system is doing and also based on the rate file that you have inputted. Here, project cash flow overview. So how much are you spending on the project? You're zero. The investment tax credit, that's obviously a big chunk here in the US. And then your revenue over the years. And you can also see depreciation here in the first 5 years. That also could be edited per your specific tax situation. And then finally, my absolute favorite, discounted cumulative cash flow. So here it shows for this project, it's kind of breaking even, at year 10 or so. And this kind of could be expected because it's, complete overbuild for 10 years. So you kind of, know you're gonna kind of run into, unfavorable financials like this. All right, so what can we kind of observe here from this example? So we were able to kind of review the financials of this project in under 30 minutes, right? So that allows users to kind of quickly review prospects at different projects in different locations and under different tolling agreement structures using different technologies relatively quickly. Another thing you can notice is that we did not specify any degradation rate. And the reason we didn't do that is because that is actually an output that is based on how the battery system is being dispatched. So through experience, we know that very rarely does a utility use the maximum 1 cycle per day. That's just a very, very rare situation. But folks can obviously want to be conservative and set this as 1. But if you had more information and use a portion of that, you can update that here. And then of course, that will result in different degradation and it will result in less overbuild capacity, which means a more cost-effective project. That's definitely a lever that you can change. Inverter capacity, although we didn't go over it in detail, but you'll see that the inverter capacity was automatically to be 119 megawatts. And this is always a unity power factor. So this is effectively 119 MVA. And the reason that's the case is because it's actually accounting for the reactive power that's going to be consumed by the different transformers on the site. So obviously there's a lot of different utility requirements. Some utilities require 0.95 power factor maximum at the point of interconnect. Others require unity. But based on that, the inverter capacity will be automatically deduced to make sure that reactive power requirements are being met both within the site and also at the point of interconnect. All right, last observation here, since we're overbuilding for 10 years, the IRR is not as attractive as what is common out there. And you can know that by seeing that more than 50% of net present value cost is just the DC block cost, right? So that's a big indicator. So where do we go from here? If this were kind of a real project, there's definitely a lot that could be done to optimize it. For example, updating the deployment strategy. You can use the augmentation optimizer to optimize when you're deploying that the different phases of augmentation for this project. Benefit from reducing costs of lithium over time. Second thing you can optimize is the battery selection. So you can try different battery OEM models. So here we just ran a generic battery model for LFP, a 306 amp hour cell. But if you're one of our Plus users, you can definitely try the different OEM models here to see which perform the best and result in the least cost. You can also try different technologies. Maybe you're a utility and you have some flexibility to try different long duration energy storage technologies. So you can try nickel hydrogen, try zinc to see if they result in better financial outcomes. All right, that is probably it for this case, and just open it up for questions here.
Yeah, we have some questions came in on the Q&A. So Mymina is asking, does the report show the overfill ratio?
Yes, so here in the report in this table shows the installed capacity here, right? So here 557 megawatt hours installed battery capacity, and at the POI that translates to 467.8 megawatt hours. Okay.
All right. Yeah, another question about, is the cost based on the actual equipment costs price or the scaling of existing projects?
It's based on actual equipment costs, and that's per the financial model that you specify here. So here we're running a generic, financial model. You may want to update these values based on any quotes that you receive. So here for the battery cost, you can update this if you have kind of a firm quote from an OEM. For the PCS cost, you can update this value here, or if you would like a different assumption.
We see you have a couple of hands up.
Okay, I see Nikhil, go ahead.
Yeah, hi, Sherif. Sorry, I missed the initial part. I had just one query with respect to how exactly you are considering the degradation for different C rate and for different cycles. Is that something which we need to collect from the supplier, or you are having inbuilt model? So I just needed to understand.
Yes, yeah, very good question. So you don't need to really input anything for degradation because that is already built into the battery model. So the way that the battery model reacts to different C rate, different depth of discharge, being left at a high state of charge, a low state of charge, that is all built into the BTT file in the degradation model here. So you really don't need to kind of specify a certain degradation rate per year. It's automatically deduced.
But like the only confusion where I had is, how do I know that that value matches exactly with what I'm going to buy from XYZ supplier? So anyone, maybe a BYD or maybe a Goshen, anyone. So how do I ensure that what you're considering and what he's going to offer me, considering that today we are going with 314 AH, say for example, next year he's giving us
Yeah.
So,
I
that's what.
understand the question. So for each of these models that are here, especially the OEM models, there's a validation report that shows the OEM data that was used, OEM or third-party testing laboratory data that was used to build the model.
Okay.
So it's fully transparent in front of the user. You can also ask your OEM to provide you with a BTT file. We're working with a number of OEMs right now to develop BTT files for them. But yeah, that's kind of the way to do it. And you can also create your own BTT file.
Yeah.
You can create your
Sure.
own BTT file using the help documentation. In the
Got
help
it.
documentation, there's a battery model construction guide. So you can interact with your OEM to just fill out the values in the model. And that way you have kind of the OEM's blessing on the model.
Got it.
Additionally,
And,
we've been using that data, results that are produced from Storlytics have been third-party validated by EPRI. They did this kind of benchmarking analysis in late 2024, and we were very kind of proud to see that our platform performed the best among the 3 that were tested. But we definitely always advise people to be skeptical, do your diligence, ask if you're one of our users, ask for the validation report to inspect it yourself and make sure you're comfortable with the results.
got it. And just a couple of things to add over that. Say, for example, you talked about that it will generate a model on its own. But say, for example, we want to have different combinations of PCS of different ratings or probably with a different MV transformer. So do we have flexibility to do that, or no, it will follow as per your default instructions or whatever you have programmed for?
Well, yeah, you can vary the architecture of the project in the Storlytics interface. But Nikhil, I'm more than happy to kind of dig deeper with you separately to show you how you can do that. But we need to keep to the schedule here. Please forgive me for that.
Sure. Yeah.
I appreciate you understanding. All right, I'll take one last question here. Shiva Ditya, I see your hands up.
Hey, Sherif, after a long time. So one question that I have from the report is that I'm seeing that there is a DC-DC RT that you have mentioned and the energy usable at POI. So I hope that is DC AC RT that you're saying, or it's a DC-DC RT. Can you go down a little bit in the table that you are showing?
I think it was a little bit up here. Yep. Yes.
So the battery install capacity. So putting the DC-DC RT means you're putting up a battery usable capacity in that zone, in the battery POI energy capacity, or is the POI capacity with the DC AC RT that you have considered? I just want to confirm on that one.
Yeah.
Okay.
So yeah, I was saying that yes, the POI energy capacity that you see there takes that DC AC RT into account. Here in the table, we are just showing the DC DC RT. If you go to the output CSVs, the yearly file, it's going to show you both DCRT as well as the ACRT. So you have both the RTs there.
And this DCRT, you're taking it from the OEM, right?
Yeah, so the models are built taking this impact of state of health on RT into account.
Correct. And
So
also, yeah, go ahead.
If you open the battery model, right? So under cell, efficiency degradation coefficient, right? So this parameter controls how the internal resistance of the battery cell increases with state of health degradation.
Correct.
Okay.
Yeah.
And there, it's the exact formulas there in the help documentation.
Yeah. And have you guys considered for like AC block with string PCS, or it's still the DC block that you have considered right now for this model?
It's both kind of the DC block and the inverter and PCS is being considered in all the losses that you see here, right? In how this POI energy capacity was calculated. It's taken into account really everything between the battery and the point of interconnect, which includes the generation step up if it's there and the PCS.
Yeah, I'm just trying to understand that whether we are considering the AC block as well.
It is, yes.
Okay, so we have the string PCS data incorporated in your Storlytics OEM profiles, right?
Yes, you can open the inverter model here, right? And look at the efficiency tables, the apparent power capability versus temperature, active power versus voltage, and the reactive power capability curve.
Understood. Okay. Thank you.
All right. I think we can, just in the interest of time, kind of keep moving forward here.
Just maybe one last question from Syed, where he was asking about the reactive power. So he said, since you mentioned to have a immunity power factor, so an 18.8 megawatt resistive losses, if we assume a non-unity power factor like 0.9, does the model take care of inverter capability curves?
Yes. So in this example, the reactive power that was required at the point of interconnect is 0, right? So unity power factor, right? So if you kind of come here, if we open the plot viewer and we go to Q set, this is the set point for reactive power at the point of interconnect, we'll find that it's 0. Now, to achieve 0 reactive power at the point of interconnect, your battery system has to feed reactive power that is being consumed locally by your transformers, right? Because transformers are inductive, right? They will consume reactive power. So if we look at the inverter, reactive power coming out of the inverter, we'll see that it's varying here because it's based on how you're charging and discharging. Your transformers are consuming different amounts of reactive power. And to meet that reactive power, your inverter has to basically produce that reactive power in capacitive mode. And that's why the inverter capacity is oversized. When you use the auto size tool, it oversizes the inverter capacity to make sure that your reactive power requirements are being met.
Yeah, thanks.
Does that answer?
Yeah,
Okay,
yeah,
perfect.
that does answer my question. So, I mean, just a follow-up to that is, for example, many grid codes require you to operate, to have the constant active power. For example, 100 megawatt in this event between 0.95 leading to 0.95 lagging. So basically, we need to make sure that we have oversized the PCS so that we maintain 100 megawatts real power and also supply any additional reactive power if needed. Do we take care of that in the model, like any oversizing from a reactive power perspective?
Yes. So what you can do in the POI profile you're inputting, there's a power factor column here. So you can just simply put 0.95 power factor. So that basically means that you're going to be capacitive at the point of interconnect, which increases the requirement for dispatching reactive power from your inverter.
Right.
Or if, you can kind of change, have, some of the day 0.95, the other part negative 0.95, which means inductive and so on, based on your specific case.
Okay, so in this case, our inverter will be more than 118, right? It will be
Correct.
125
Yes.
or something. Yeah, okay.
Exactly.
Thank you.
Yep, sure. All right. Okay, so I think that's it for this case. Kind of switch to the next one here, which is market services applications. And Jakir, I'll pass it over to you.
Yeah, let me take over. All right, I'll go ahead and share my screen. All right, you all can see my screen, right? Yeah.
Yes.
So this case here, basically what we'll be trying to do is focus on optimizing the deployment strategy. So when the first case that Sherif showed basically focused around a 10-year overbuild, right? We are not doing any augmentation of any sort. This case here, but if you are doing a 20-year, 25-year projects, it's seldom you're gonna like oversize it for 20, 25 years. You are gonna be doing some kind of augmentation. And when you are doing augmentation, the question that often comes up is, what should be your augmentation strategy? Are you going to go with AC augmentation or DC augmentation? How often you should do your augmentation? How frequently, what should be your initial overbuild duration? So that kind of question is basically impactful because the number of augmentation you do, when you do augmentation, how much capacity you add, all this adds to your overall project CapEx and OpEx as well. And that eventually impacts your project IRR. So what we're going to do in this example, this new version, we have added a new feature called the Augmentation Optimizer. So that, based on some user input, it basically gives you an optimal augmentation schedule from the program. And in this example, what we'll see that we're going to use that feature. We'll see the results of that feature. We'll have a discussion over that. And we'll see how that feature allows us to optimize our project. Because eventually that's what is most critical. Yes, you're reducing your cost of your projects, but then eventually how does it impact your overall returns? So with that background, what we'll be doing is we're going to designing a 100 megawatt, 400 megawatt project in the ERCOT territory. Even though it's the same size as the previous project, the profile that we'll be using is going to be different. The previous project that we ran was a 1 cycle per day standard cycle. In this one, we are going to be using the market signal, right? Because every market is a bit different. There are different services available that the BESS can subscribe to. So we have added a new feature powered by our partners, Horizons and AC Energy, that allows you to import market-specific signals. So we're going to go over that. We're going to utilize that feature to create a profile, and then we're going to use that profile to design the project and basically optimize the augmentation schedule. So it's a 20-year project life. I want to make sure folks understand we are not letting it degrade. The goal here is to maintain 400 megawatt hour at POI throughout the 20-year project's life. And the equipment we're using is, in this case, lithium iron phosphate batteries. We're going to use the 280 ampere hour for this example, and then the SMA SCS 3950 up inverters. You can, if you want, iterate over these batteries and inverter models as well. But right now, I want to focus more for this example on the deployment strategy and augmentation. So if you keep the equipment the same, just depending on the augmentation strategy, your project finances kind of varies is the focus of this example. So we'll go ahead. Let me make it full screen here. So we'll do a new project. The first thing we come here, similar to the previous project, we have to specify the target energy and power. 20-year project, we're going to select augmentation here. That's the deployment strategy. And as soon as we select augmentation, you will see that these two parameters become, because now the related parameters needs to be inputted. That's required for the augmentation optimizer. On the load source, for this example, we're going to do the PS serving from the batteries. So if you switch between these two options, you will see that how the auxiliaries are being fed is changing. If we go POI, that basically means the auxiliaries are being fed from the batteries in line with the POI. If we have a separate, it's fed from a completely different meter source. We will do a T-type project here. It's a large project in ERCOT. We're going to enable battery degradation and also the temperature regulated part of the. If you select a battery degradation, you have to input an initial state of health. For this case, we are keeping it at a completely brand new battery, 100%. Then you come to the interval data. So this is where we are going to be using this time series option. So this is where we are inputting how this battery is going to be dispatched. And to get that profile, we'll utilize this new feature called generate from market signal. So what it does is if you click on that feature, it asks you to input some information about the project that you're trying to build. So first parameter here is about your project capacity, which we're doing a 100 megawatt project. Then it asks you what is the duration of your projects. In this version, you can select 3 different options. So we are selecting a 4-hour battery. Then what you can do is in the select market signal, it allows you to select a typical market signal in that market. So you'll see the versions that you have has ERCOT and the PJM, and we're also adding new market signals all the time. So in my versions, you have CAISO, MISO, and other market signal as well. So signals that we're getting here is basically coming from our partner, Horizons Energy and AC Energy, and what they do is they basically predict the optimal dispatch of the battery in that market and give you a representation of how a typical battery is going to dispatch in that market. So in this case, we can go ahead and select, let's say we're doing ERCOT, so we're going to select an ERCOT market signal 4-hour. And as soon as you select it, then you can select the year that you want to be the base for your design, right? So this is where you can select that, yeah, I mean, I'm probably on a design for 2027, or if you want to look maybe more into the forward curves into the future, you can select a more later year if you want that to be your best case. Once you have done that, then you go ahead and you input a file name. And you will see that generate POI profile is going to become enabled. And you go ahead and click it. And it will give you a message that POI profile generated successfully. And you'll also see that POI profile being selected here. Previously, there was no POI profile at this location. If you want to take a look at that profile that it created, what you can do is you can come here into the POI profile diagram. So there are different options. So you select the POI profile. So it is going to show you that this is what the POI profile that we picked looks like. So looked like for this signal on the summer and the winter, you're doing more energy arbitrage kind of services, and then basically energy services. And then in the shoulder months, you're doing more of an ancillary service. All right. So once you have selected this profile, so your task is done. So you have defined that yes, I'm going to build a 100 megawatt 4-hour battery, and this is how I plan this battery is going to be operated. So now you go about sizing this project for this. There is one more input that you have to give, which is the TMI3 file. So you can come here and you input your TMI3 for Texas. If you want it to be more specific, so what we have already in the library is a typical file in Texas. If you want it specific to your coordinates, project location, you can download that as well from the NREL website. If you give the coordinates, it's going to let you download it for that exact site. Once you have input those two, then you go to the equipment tab. So this is where you come in and you select which battery you plan to use, inverter and enclosure models. So in this case, we said we're going to use the 280 ampere hour. So we select that one. Inverter, we'll use the SMA SCS 3950 up. And then on the enclosure model, we're going to use the generic liquid cooled LFP. And these things are completely user dependent, right? So depending on your need, you can select any batteries and inverters that you want to design for. And then if you want to find out the best battery and inverter for your solution, you can iterate over them as well. Then you come to the system specs. So here you see this is blank, so you don't have to do anything yet here, and the operational can be blank as well. What you're going to do is you're going to jump to the augmentation. So as you come to the augmentation tab, you will see by default under augmentation schedule type, the augmentation optimizer is selected. So folks who are familiar with our previous version will see that in the previous version, the augmentation schedule type, we only allowed user input. With this new version, this augmentation optimizer is a new feature. So in this, if you select that one, what you will see that this is grayed out. And basically, if you run the optimizer, it's going to produce an augmentation schedule and populate it here. So what are these parameters on the augmentation optimizer, right? So let's go over them one by one first. And also the objective of the augmentation optimizer. So what the augmentation optimizer is doing is based on the project financial information that you have given, it is trying to find the most cost-effective option that basically meets your 400 megawatt hour POI capacity through the 20-year project life and does it in the most cheapest way in terms of net present value. So it combines all of your equipment models and run hundreds of scenarios in the back end and is basically looking for the cost of each of the solution and then eventually suggest you the one that is most cost optimal. So if you come here, first thing you have to input here is the type of augmentation. You can either choose AC augmentation or DC augmentation. So obviously in AC augmentation, you are adding inverters as well as battery blocks. In DC augmentation, you're just only adding battery blocks, so no inverters have been added. The number of inverters remains the same. Now, to describe all this, what are these parameters and what are these options? So each of the parameters has two options, user-defined and Storlytics optimized. We will refer to the PowerPoint here. Yeah. See if I can make it full screen. All right. So this will help us to understand what each of these three parameters are. So the first parameter is the augmentation interval. So that basically means, if you see on the screen here, what is the duration of your initial overview? Are you gonna, the initial system that you're putting in, is it gonna take you for 3 years, 5 years, 7 years, 10 years, whatever the years? So whatever you put in here, so in this case, we put in 5. So that basically means that the initial augmentation interval is 5, right? So all the scenarios going to be looking at, all of them going to maintain that a 5-year over for the initial system. The second parameter is the number of augmentation. But what does mean is that, so we get 3. So that basically means all the options you're going to look at is going to maintain the number of augmentations to be 3. So it's not going to look at 2 augmentation, 5 augmentation, 1 augmentation, those scenarios. It's going to look at only number of augmentation to 3. And that's like if you select user defined, right? So that basically gives you some choice to basically outline your preferences. Maybe depending on your project or your team, you might want to do less than 3-year over. So yeah, things like that you can specify if you want the program to not search everything exhaustively. And then the last parameter, which is the minimal augmentation interval. So that basically means that the minimum duration between 2 augmentation cannot be less than this, right? So in this case, we set 4. So you will see if we are doing an augmentation at year 5, we can do either year 9, 10, 11, but we cannot do at year 8 because this is controlling what is that minimal augmentation interval. Now, for each of these parameters, you have 2 options. So if we go back to our software here, if you select, let's say for the augmentation interval, select the Storlytics optimized. So you will notice that it grayed out that field. So in that scenario, it is not an user input anymore. So the program in the backend is gonna try out different initial augmentation interval. Like I was saying, it's gonna try out 1 year, maybe 2-year, 3-year, 5-year intervals, and then it's gonna look at which is the most cost effective. There are a few different things in the interplay here, right? So one thing is that if you're expecting your cost of your batteries to go down, then it might be beneficial for you to not put in a larger battery to begin with. But then you also have to take into account that if you want to do too many augmentations, and we know that for lithium-ion batteries, initially they degrade much faster than the later years. So there are some trade-offs that you are taking in there. So when you combine this degradation impact, the RT impact, along with the cost impact, you start to see that all these different options causes you a significant difference in the overall cost of NPV. So for me to illustrate this fact a little bit more, that because the question might be that when should I select Storlytics optimized, right? So I wanna expand on that a little bit. So if you, let's say, select all these 3 parameter user defined, so you're being very prescriptive, right? So you are actually then narrowing your optimization search space. So you're only looking at handful of scenarios. So for example, in this case, we defined all these 3 options user defined. So in the backend, the program looked at 10 different options, because if you are being prescriptive with all these 3 parameters, there is not a lot of scenarios to look at, right? So it looked at 10 different options, and it saw that the difference between the most expensive option and the least expensive option in terms of the augmentation schedule is like around 1%. But if you, let's say, make some of this parameter Storlytics optimized, so here we made 2 of the parameters Storlytics optimized. So we made the augmentation interval Storlytics optimized, and number of augmentation also Storlytics optimized. So now the program in the backend is not just looking at 3 augmentation schedule, it is looking at 1, 2, 3, 4, 5, and others, as well as on the first augmentation interval, that initial overbill, it is looking at different combination as well. So here you can see that in this case, it looked at 58 different combination, and it came out to be the one that is most cost effective is like 93%. So there's a 7% improvement, like difference between the least cost option and the most expensive option. And basically insight that I want you all to take from here is what happens based on this. If you can set everything to Storlytics optimized, and that basically means that you are running a lot of scenarios and it's going to take you some time. Or if you can reduce the search space, be more prescriptive, that's going to cost you less time. But the possibility there is that you might miss out the most optimal solution. Here, we are running like almost 96 scenarios, and you can see that between the least expensive and the most expensive, the difference is almost 14.5%. And all this depends very much on the equipment you select, performance, but also some of the cost assumptions that you put. So once you go ahead and basically you run the augmentation optimizer, what it is going to do is it takes some time to run it, and basically it's going to start running. And it's going to take some time, right? So I'm actually not going to run it. I already basically pre-ran it and generated the augmentation schedule. So in the essence of time, we can load that example case and we'll proceed from there. But essentially what this is going to do is once it's done running, going to input that augmentation schedule here, and then you'll be able to run the project and basically see the other parameters. And once it's done running, it's also going to finish up there's this show results button is going to become enabled, and you will be able to see that the augmentation schedule that you are getting is that like really optimal. So one of the graphs that you're going to be getting is this one. This is one graph. So that tells you that how much of a cost differential you're getting for the optimal solution. Second graph you're going to get is that, because one thing you wanna really maintain that all this augmentation you're doing, your eventual goal is to maintain that 400 megawatt hour, right? And you can see here that the optimal one that it's proposing is saying that your first augmentation interval should be for 3 years, then you come into another one in 7 years, and then do another one in 12. And you are able to maintain your POI capacity, right? So that gives you the confidence that, okay, yeah, we got an augmentation schedule that maintains my capacity. And then the last thing, the augmentation will give you the state of health. A lot of times what happens nowadays in the calculation or kind of the practice is you get a one generic degradation state of health profile, and you basically apply that for all of your augmentation schedules. So you basically apply the same state of health degradation for all the augmentation schedule. But in reality, that's really not the case. Each of these augmentation phase is going to have their own degradation. So here for the optimized run, it gives you the state of health for each of the individuals run. So you have your initial build, which is the blue one. Then at year 3, you add a new battery through augmentation. This one is giving you the degradation for that phase 1 battery, and then phase 3, so on. So the impact of adding augmentation on degradation is really taken into account in the augmentation scale optimizer. What happens is that you get an initial augmentation or state of health prediction based on your uses, but as you add more batteries, your initial system is not performing the same way. It is having to do less, right? Because now you have had more inverters and maybe more batteries, so the burden on the initial system decreases, and that's going to cause it to degrade less. So that interplay with augmentation and degradation is captured to the augmentation optimizer. Okay, then the next step for us is we're going to go ahead and load that profile. So I'm going to abort the augmentation optimizer because it does take some time to complete the file and go to open. We'll open the example ERCOT BESS _ AC. So that's the AC augmentation solution. Just double click on that one. And it's gonna load that project for you here. So we are basically just picking up from the output of the augmentation optimizer. So once the augmentation optimizer is done running, it basically generates that augmentation schedule. And then what we're going to be doing is we're going to be coming to the financial and we're going to be inputting some of our revenue options. So for the revenue, we have two different contract types that is allowed now. One is a tolling agreement and one is a margin market. So in the tolling agreement, you select tolling agent service, contract terms. Then there are some tolling agreement related performance matrices. So you can choose whether to include all of these or you want to do one or another. So first matrix is regarding the energy capacity. So most of the tolling agreement is going to have some kind of LDs associated if you fall short of your contractual capacity. So what it does is, if you have this feature on, it looks at what is your year-over-year capacity, it compares it with your target capacity, and if you are falling short, it is calculating a penalty for falling short. Same for your RTE. So we have had it set at 88%. And once you simulate the project, if the project RTE is below this, and it's going to go down with time, so time your RTE LD is going to keep increasing. And then the availability factor is also in there. So you can specify what's your guaranteed LTE availability, and then what availability you're getting from your suppliers. So you can take the impact of availability in your revenue penalty calculation as well. So what really it does is basically it allows you to connect your system performance with revenue. So if your system is underperforming in terms of capacity, in terms of RTE, now with the feature help of this, you'll be able to see the impact of that on your potential LDs and your revenues. Now, these things are coupled with some of the parameters under the financial model. So in the financial model, there is a cost piece, but then there is a revenue piece too. So in the revenue piece, in the tolling agreement, this is where you can input your fixed price for your tolling agreement in dollar per kW month. And you also get to set some of the rates for these LDs. So all these are customizable and you can set it depending on your project and your financial models. So you do that for the tolling agreement and you have a separate for merchant market, which I'll cover later when we're doing a merchant market example. All right. Now for the augmentation optimizer run.
Jakir, real quick, for the folks that don't have kind of base or plus to be able to run the augmentation optimizer, can you tell them what to do to input the optimized schedule?
Yeah. Once this runs finishing, I'll tell the folks about that.
Cool. All right, we got a hand up here. Sayed, go ahead.
Yeah. Hi, Sherif. Hi, Zakir. My question is, since this is a tolling agreement, why are we doing AC augmentation? What is the incentive of adding more inverters here? Shouldn't we go for DC augmentation in this case?
Yeah, so that's the exercise, right? So we'll look at both AC augmentation and DC augmentation, and we'll see which one is most cost effective. And then based on that, we're going to decide with this project, which one we're going to go with. And yeah, you're going to see like the DC augmentation, the cost is going to be a bit less because you have less inverters.
Okay, and another question was, since we selected the market signal in this case, but since our use case is tolling agreement, so as a battery owner, there is no incentive for me to, you know, I am being paid for 1 cycle a day, irrespective of whether my battery is idle or I'm running it at, you know, full speed. So do I really need to optimize if I'm purely on a tolling agreement?
Yeah, if you are purely on a tolling agreement and you're doing 1 cycle a day, then probably not, right? You basically are just going to do the standard cycle and do 100 megawatt and then just go about that. But in this scenario, we wanted to show the impact of market signals. So if you're an owner and operator, think of it from the owner perspective. If you are subscribing for a tolling agreement, you know, see from your perspective that this is how I plan to operate it in the market, what that pricing of my tolling agreement needs to be. So on the owner side, the owner is going to be able to evaluate that the pricing that they're signing up for, is that going to be profitable for them?
Okay, so we're talking about energy arbitrage there, or only that use case, or are we stacking different revenue streams?
So the market signals that we are getting from our partner, it's a co-optimization of energy as well as ancillary services. So the profile that we are getting, this profile that we get, is a combination of energy arbitrage. So you'll see that in the summer and the winter month, it's like those energy arbitrage kind of profile. But then in the middle here, there are sometimes in the shoulder month, it is doing not as like those frequent energy arbitrage, rather doing small burst of discharge, which is basically ancillary services.
Okay. Yeah, and these are the power profiles, not the price signals, right?
Yeah, these are the power profile. There is a place you can import the price signals. So if you go to the financial model, go under merchant market. So this is where for the merchant market, you can import your pricing, right? So this is the price signal. So if you have your own pricing, it's just a CSV file, you can add it into that folder, and then you're going to be able to select that. Yes, and then you can also select if you want those pricing to escalate year over year or not. So yes, those are the two levers you have available. You can bring in your own prices, and you can also control if there are any change in those prices.
Okay, understood.
Perfect. So once it's done finished, so for the folks who basically do not have the optimizer, you can select the user input option, and then you will be able to select from the drop down the profile that we're using. So the augmentation schedule that got created from the optimizer, we have provided that to you. So you can go ahead and select the augmentation schedule, select that option, and then you can go ahead and run your scenario. Once this run is done, you can click the generate report button to generate the report. So I have the report pulled up here.
Hey, Jakir, we have a question from Spartak. Spartak, take it away.
Can you hear me? Hi.
Yes.
Sherif, Jakir, thanks so much. A quick one. So you have a battery that has both contracted and merchant revenues. And let's say I have FPA, or PPA was, for 60% of my energy capacity, right? And then I have, the remaining ones, which I'm, selling for the merchant markets. So is it possible to simulate this scenario with this tool?
Yeah, it will be. Let me see real quick. Okay, this one. So what you're gonna do, Spartak, is that you're gonna go to the financial and you're gonna select the merchant market, right? As soon as you select it, it allows you to give an option for capacity payment. So even though we call it capacity payment, you can term it as a resource adequacy like KISO or a PPA. So here, if you, let's say you are gonna only sign up for a 10-year capacity payment and your overall project is 20-year, you're gonna do like the whole 20-year, you're gonna do market participation, and only 10-year of that, you're gonna do capacity as well. So you can run it that way. So if you go ahead and let's say we run it real quick, I'll show you right now real quick here. A minute, but yeah, while it opens up, if there is any other question on the Q&A that I can address right now.
Apologies for jumping in but just a follow up to Spartak's question. I think we are splitting the time here, like 10 years for capacity contract and 10 years for the merchant. But I mean, what if we have to split the installed capacity? Like we have 400 megawatt hours or 100 megawatts, and we are reserving, let's say 80 megawatts for capacity and the remaining 20 for merchant. That kind of revenue stacking, multiple stacks at the same time.
Yeah, so right now that option is not supported. Yeah, I understand what you're saying. So you're saying like basically essentially two subsystems. One is going to be contracted with a tolling agreement or some sort.
Yes.
Another one is like just going to be market participant.
Yeah, like many developers also, for example, if they win a capacity auction for 100 megawatts, but they install their battery for 200 megawatts with the intention that 100 will be reserved for capacity market and the remaining 100 they will use for something else like arbitrage or other markets available, spot market or whatever it is. So basically they're stacking revenues at the same time for the total life for 20 years.
So you can run that as two separate projects.
But don't we have to optimize the dispatch in that case?
Well, it depends on how you're planning to dispatch them. If there's some interrelation between the service one is doing over the other, then yeah, it's kind of a very, very specific, complex scenario you're describing. But if you're dedicating a certain capacity for one service and another capacity for the other, it's basically as if you have two battery projects that just happen to be interconnected at the same point of interconnect, then that's where you can kind of leverage two different project simulations.
Okay. I mean, we are kind of simplifying it. Like we are treating two revenue stacks as two battery projects and then treating them independently. Well, okay. Yeah, understood.
Okay, so once that's done, we do generate report. Jump to the revenue stack here. So yeah, what you see here is that you have those market revenue coming in the forms of energy revenue. And then on top of that, for the 10-year, you did the capacity payment contract. So you get a stacking of two different type of contracts here. Yes. Does it answer your question?
Yeah, thanks. I think so.
Okay, so in the report, initial segment goes over the power and energy adequacy. You can see in terms of power, we are meeting the requirement. In terms of energy, we are meeting it almost 97.5% of the time. That's pretty good up there. And then what we do is we go into the system efficiency. One thing to point out that's new in this new version, we added the option for cycle RTE as well. So now you see two RTE reported. One is a simulation RTE, another one is a cycle RTE. So the difference between the simulation RTE and the cycle RTE is simulation RTE is based on your dispatch profile. In the dispatch profile, you can already observe that there are cycling, but then there are idle time as well. Even when your system is idle, it is providing for your auxiliaries and other things. The simulation accounts for that. On the cycle, it doesn't look at idle time. It's just a typical full cycle where you charge the battery from minimum to maximum and discharge it from maximum to minimum. It calculates that based on that. We have the losses in Texas. Some months were consuming more auxiliary losses, and then we had the throughputs and others. So I'm going to jump to the main part here. The main thing we wanted to check was, are we meeting our POI requirement? We are meeting our POI requirement. So once that's verified, we jump to our next section, which is basically the cost. So in the cost segment, you will see that there are different components to the cost. So there are a couple of new components that have been added from last time. So we have the GSU and the high voltage breaker cost added. So if you are doing a T-type project, there is an input for these two parameters in the financial model, and based on that and the size of your project, those costs are going to be accounted for. And you also have a balance of plant cost to account for your EPC cost. So that now really the cost that you get from the software is really the overall project cost, which pretty much takes everything related to project into account. Then it gives you the breakdown of your OPEX. So this is an interesting chart. So year over year, I think Sherif also mentioned that is the OPEX going up with time. So escalation. So you kind of see that the OPEX is it's escalating over year. There are 4 different components. So the light blue here is the energy loss. So that's the part basically is your auxiliary consumptions. The second part is the state of health guarantee. Other known terms for that is performance guarantees and LTSs and preventative maintenance. So what this is showing is that first 3 years, it didn't have any state of health guarantees, mainly because in the file that we utilized here, if you go here, you will see that the standard warranty terms are 3 years. So first 3 years is already covered. So there was no extra you had to pay for the state of health guarantee. After that, when you're going for long-term performance guarantees, you're having to pay for it, and that price is taken into account. And then you also have here is that we did 3 augmentations. So year 3, 7, 12. You can see the breakdown of different components of your augmentation. So your cost of your battery, which is the green one. We did PCS. Because this was AC augmentation, we added inverters as well. So that's the orange one. And then on top of that, there are some plant integration and other costs related to augmentation, which is the gray one here. So it really gives you a good breakdown of your OPEX and how the operational cost varies over the years. Then it takes you to your revenue. We are doing a tolling agreement, so it's a fixed revenue, not changing. But on the negative axis here, what you see is the different LDs. So one of the things right away is that our availability LD, because we set our target to 97. I think it was 97, and then the actual availability was 94. So it is a straightforward calculation there. And then on the RTE LD, if you look at our target was 88%, and what we get here to begin with we jump to the section is around 85.48%, right? So with time, it's going to go down. So we are falling short of 88 at the initial years, and then with time, it's just increasing. So you'll see the effect of that LDs here in the revenue chart as well. If you focus on that light blue one, it grows with time. So once you got your revenue, you got your complete project cost. Now it's about looking into the cash flow. So in this case, it is giving you your initial capex. We have included ITCs to be applied at year 0. That also a 5-year makers depreciation, along with the green one here showing your every year net revenue basically. So the years where you had to do augmentation, you will see that net revenue are pretty low. And with that, it gives us a unlevered IRR of 9.5%. The IRR reported here is before any kind of debt finance, debt equity, other kind of financing, just the levered IRR of the system, which takes a cost, ITC depreciation, and revenue. Then there is another chart that gives you your payback period by specifying a certain discount rate. If we apply a 5% discount rate, the payback period is going to be 13 years. So I think that covers the base case for the AC augmentation. We ran the augmentation optimizer, we got an augmentation schedule, and we got an unlevered IRR of 9.5%.
Hey, Jakir, real quick, we have a question from Syed. Why is the availability LD applied? When was the BESS unavailable?
Yes. So that's an user input, Syed. So we have a guaranteed LD of 97%. And the actual availability is also a user input in this case. So we said the actual availability is 94, and that falls below the 97. That's what triggered that availability LD. Right now, this is not something calculated from the program, that availability, because that's very much dependent on maintenance and quality of the product being supplied. But a lot of our users wanted to see the impact of that in the revenue stack. So we made it an input. Typically, if you're contracting with Sungrow, Teslas, and others, they are giving you a contractual LD, like an availability percentage, and then you are signing up a PPA with a certain guaranteed availability. So you can input this number based on what your suppliers are giving. Here I had it set low, just to show that point that your availability LD gets triggered if you have a lower value. All right, so with that, let's just go to the next case. So the next step for us is to do a DC augmentation, right? So we ran an AC augmentation, we got the optimal stuffs, we got our final results. Now we're going to switch to a DC augmentation. So all you need to do is come here and make it to DC, run the augmentation optimizer. It's going to generate a schedule for you, and then you're going to do run. Since some folks might not have access to the optimizer, we give you the project file. So if you open the project, which is ERCOT example base _ DC, so that's DC augmentation, open that one. So I already pre-ran it and populated that one. And then you basically go ahead and run that. While it runs, I have the report up, so I'll go over it. This was the DC. Augmentation after it runs as well is going to show that it maintains the capacity. Even though the initial overbuild and the number of overbuild are similar to AC, when the augmentation was done is a bit different. So in case of AC, the first augmentation was done year 7, and I think then year 13 or 12. In this case, because the way the system is executed during DC is different than, and you have less inverter, less losses, that causes your degradation to be different, and that causes a couple of years of shift in your optimal profile. So yeah, we run that one, and then let's go back to the PowerPoint here, where we have some observations to share based on this. So first observation is that we are showing is that the fact that I was talking about is about the degradation, that if you would not have done augmentation and you don't take the impact of augmentation on degradation, you might be overestimating degradation, right? So to showcase that point, what I have on the screen here is you have this red one. So red one is you didn't do any augmentation. You had that system, you just ran it, let it degrade. So no augmentation is done. So that's what gave you the red one. And then this green one and the blue one are our AC and DC augmentation. So what you will see here is that at year 3, up until year 3, all of them were on top of one another. At around year 3, now that you added more battery, now your initial system needs to do less. That means it's going to degrade less, right? The C rate is less, the depth of discharge is less. So now it is having to do less. So you see that from year 3 onwards, that your degradation starts to decrease. So for the AC and DC augmentation case, the degradation rate slows down as you are adding more and more batteries and inverters. And you can see up until year 20, it's not as less. It's like almost 3 to 4% difference compared to your initial system. So now what the detailed nuance here is typically when you are designing it, you are getting that grade 1 from the provider or the OEM's one state of health curve, and then you are basically applying that for all of your different degradation steps. And that's gonna lead up to you with a more conservative system, which can be 3 to 4% off than what it actually should be. So that's one factor, and that's very critical that this whole
Jakir, let's address some questions in the Q&A here. So first one here is an augmentation cost for DC blocks and PCS should be reported as CapEx.
We have heard different opinion on that one, to be honest. So our philosophy is we consider it as part of the OpEx. So yeah, I think most of the folks, the project that we worked on, typically what we have seen costs are being considered as part of the OpEx.
I mean, Spartak, I have not run into a case yet where, you know, the developer or project owner is paying up front for augmentation cycles that are going to be done in the future. That you know, not to say that it doesn't happen, but we have not encountered a case like that.
Yeah,
Is that something that's common?
I think especially from European perspective, that might be something where we could, you know, apply a different taxes scheme, you know. But I'm not an expert in that. I just raised the point because I've seen this, yeah, potentially because it's a kind of a capex, it's the equipment, therefore might be more relevant. But yeah.
Oh, okay. So you're talking about like capitalize it from an expense standpoint for perhaps like a utility structure, so it could be rate based, for example. Okay. Yep. Now I get you 100%. Yeah. So this is kind of speaking only, you know, just from a pure like cash flow standpoint. But yeah, that is a really good point that in different financial structures, there's a different recovery mechanism. So it's probably very important to mention at this point that all these financial results can be exported as CSVs, right? So that allows a lot of flexibility for different types of organizations to apply their specific financial model mechanisms. A lot of folks have a kind of a converter like in Excel where they export the CSVs and it automatically populates to their kind of financial model. That's what Jakir is going over here, right? So you see year by year, each type of expense is laid out here. So that gives a lot of flexibility, hopefully.
That's great. Yes, that's really flexible. Thanks.
Yep. Perfect.
All right. So that's that. Do we have any other question that we can take?
No, a lot. Okay. Can you use different principal state of health curves for different battery phases?
Yes, I mean, that's what the optimizer does, right? But everything is governed by the battery model, right? So depending on the battery model, the one that you selected, if you utilize that model, each augmentation phase is going to have different degradation because everything is going to be used a little differently. As you add more capacity, you see a stepped up discharge, throughput, so those things are going to vary, and you'll be able to see the impact of that. And then if you really want access to that state of health, you can do that. If you go to the yearly data, the raw value of the state of health for each of the phases are reported here. So you will be able to see the raw values.
So, and just to make sure it's fully clear, the rate of degradation in each of these phases that Jakir just highlighted is different because the rate of degradation is based on how exactly each of these phases was dispatched, right? Which is different. Each of these phases have been dispatched differently, right? So just want to make sure that's clear. All right. Next question here. Do you have plans to add market signals for EU market? We're definitely open to it. So this is the first version of Storlytics with, directly connecting, to like a partner API, Horizons Energy. These are the makers of Encompass software, IRP software here in the United States. Very, very trusted company. So currently no concrete plans in Europe, but we're definitely open to it. And we'd love to kind of mimic this model with other entities in Europe. So if you know kind of a company, just please feel free to put us in contact with them. We'd love to input their data. All right, okay. Next question here. The market is not included in the list. The creation of the market signal is within the software subscription. What regions could cover? Oh, this is actually a very good point. So the market signals that are shown in generate from market signal here, when you like this drop down, this is basically a CSV, right? So you can go into your Storlytics user file directory, and let's say your project is in Europe and you have access to data from a company that does this type of dispatch optimization and forecasts it, you can just add that here and it'll show in the drop down and you can use it directly. As long as it just follows the same format, that you can definitely use it. Right? Hope that helps, Oscar. Anton, is it possible to have at a convenient? But I think that's all the questions. I see we have a hand up here. Yeah, go ahead, Anna.
Hi, thank you. I wanted to go back to the OpEx versus CapEx question and just say that at least in the US, I don't, for tax purposes, like the equipment has to be depreciated just like the initial investment. So, and I'm not, I'm trying to figure out if that's a different depreciation schedule, which I think it probably is without the ITC. So like a 7-year, 12-year depreciation. So, and I know that's a comment, but my question was, when you do that augmentation, is there, so like the initial investment will have, construction financing and all that kind of thing, like maybe a 3-year construction schedule, like interest on the construction financing, that kind of thing. Does augmentation have similar financing parameters? And similarly, you have debt, equity, tax equity. Is it basically that the augmentation is entirely equity, like just a cash outflow without any kind of financing parameters? Does that make sense?
Yeah, so right now, Anna, we are not taking those debt equity and other equity into consideration, right? So that's why we kind of made it clear that this is unlevered IRR. Okay. So we don't have those financing layers added on top of it. So it's basically what it is representing you is that cost. So when you see this in the augmentation, it's taking the price of lithium or battery or PCS at that year, depending on your forward curves. And it is telling you that in that year, this is how much it's going to cost you. But any kind of extra payment that you have to do to finance that, that's not part of it.
But
So-
that's where, oh, go ahead, Anna.
Sorry, I just want to say, I guess my real question was because y'all seem closer to industry than I am. Do you have recommendations about that? Like, what have you actually seen as far as how, excuse me, utilities and developers finance augmentation versus the initial investment? Like, how would you treat it ideally?
For utilities, they do not like augmentation, especially regulated utilities, because they have some issues kind of capitalizing on those augmentation expenses, whereas with overbuild, like they can capitalize every cent of that year zero investment and rate base it. For the other part of your question, I'm not really sure. On the finance side, we've seen so many different structures, so can't help there.
Okay, thank you.
Sure. Now, for the first part, if you wanted to apply different finance structures, that's where the output CSVs help, because the core of really every financial mechanism you have out there is the expense, right? And that's kind of being putted in the CSV with differentiating the type of expense in each year, as Jakir showed. So then you can use that as starting point and apply more complex financing mechanisms. Okay, we have another question here from Sandro. Go ahead.
Yeah. Hi. I have a quick question about the components, the cell, for example. If we want to implement a new cell, let's say to compare projects and so on, so that you have what seems to be a very complex degradation parameters and so on. How can we implement this on a new cell? Do you have any documentation on that?
Yeah, so in the help documentation, there's a battery model construction guide. So once you open that, you can kind of see like step by step, how can you create your battery model? So what parameters you need to fill out and so on.
This is not available for everyone, right? Because, for example, in my help,
Correct.
it ends at auxiliary load model.
Correct. So this is the battery model construction guide includes a lot of intellectual property that we do not share with trial users, but this battery model construction guide is there in the full and plus versions. Yep. But if you'd like a deep dive, we're always happy to kind of have sessions with the users to kind of deep dive on how to develop, how you can use that battery model construction guide to develop a new battery model.
Thank you very much. I'll reach out to the team.
Yep.
Okay, so did you cover all the questions here before I move on?
Yep, I think that's it.
So yeah, so then the second observation of the augmentation schedule, we kind of touched a little bit on there, that the AC augmentation and DC augmentation, they are not adding capacity in the same year. So you'll see that AC augmentation at year 3 added, but didn't add it as much as DC augmentation needed to do. And then at year 7, AC augmentation was doing phase 2, but for DC augmentation, that was year 8. And then here, year 12 versus year 14. So really, because depending on the solution it is running in the backend and the interplay of those complex dynamics, it is determining what is best for what configuration. We covered the RTE part in detail, so I'll skip that. That comes to our cost of ownership. So we saw that compared to the AC, the DC augmentation was around 1.2% expensive because you needed similar amount of battery configuration. For this example, you needed similar amount of DC battery to be added, but on the AC augmentation, you had those extra inverter costs that are not there for the DC. So the DC came out to be more cost effective. And then when you take that and look at the impact of that on your IRR, DC gives you 9.7% compared to AC giving you 9.5%. So for this project, with the set of assumptions that we have, we're going to go with the augmentation. That's going to maximize our IRR. And then the last case I had was just to show that, how you can utilize this to compare different market structure. We already ran it, that we ran a tolling agreement, and then I went ahead and ran a merchant market with the numbers. And really what the merchant market shows that the revenue are not as much. You are actually not going to be making any profit. It's like negative 1.4. So for this structure, with the inputs that we had, is basically telling that this merchant market option is not going to be economically viable, right? So when you are looking at different contract types or trying to set pricing for different type of contracts, you can utilize this tool to understand where those prices needs to be for you to hit your target IRR. All right, so the next one that we have planned is designing a BESS for data center applications. So what we're going to do is now there is a lot of talk about flexible data center design, adding solar plus storage to add some flexibility so that if you are having a lot of network upgrades because of interconnections and delays to your project, you can basically try to bring your interconnection limit down and be flexible in the time of high peak time. The project that we have planned for this one is that we are designing a 100 megawatt data center load. The utility basically for this case, let's say they cannot connect 100 megawatt without a lot of upgrades. So they could allow up until 90 megawatt. So the owner here, in this case, is looking for a combination of solar plus storage to see if they can bring the overall site load down to 90 megawatt and not exceed that. So in that way, they can still get connected. And in those high power scenarios, they are going to be able to use batteries and storage. One thing to mention is that we are not considering any kind of data center load management or algorithm shifting or time shifting of algorithms. So right now, this exercise is mostly if you want to add solar plus storage, what should the size of your storage that could allow you to decrease your interconnection limit from 100 megawatt to 90 megawatt. So we have a 90 megawatt interconnection limit, 100 megawatt of data center load, 75 megawatt of PV, and we want to determine the best capacity by running the simulation through Storlytics. So what we're going to do here is we are going to go back to the software and we are going to open an example file for this. We go under File, open example underscore data center. Once you load it, we're going to jump to the battery profile creator module. So we have talked so far, both the examples we did focused heavily on the battery system modeler. We also have this module, the profile creator, that basically allows you to size your batteries and systems for applications, right? So we're going to come here and we're going to select microgrid demand. So you come here and select micro demand. We're going to input 365 days for this exercise, time is step of 1 hour. And we're also going to select this option of copying the output profile for it to be an input to the battery system modeler. Because the output of this module is going to be, this is going to tell us how big of a battery we're going to need from a point of interconnect perspective. So it's like, do we need a 10 megawatt, 40 megawatt hour battery for this application, or we need a 100 megawatt, 800 megawatt hour battery, right? So what this module is going to help us answer is that, what should be the size? And then it's also going to give us a profile that, your battery is going to be operated at this way. And then we're going to take those two input, we're going to input that into this other module and complete our design. So in the first module here, once you are done with the general tab, jump to the microgrid demand. If you have selected microgrid demand here under apps, your microgrid demand tab should become enabled. First thing you load in is the load profile for the data center. So if you click the drop down, it should already be populated, but if you want to bring your own profile, you can come in here and basically you can load your own profile. So right now we are using this one, data center example load profile. Let's see. The red one here is our data center load, and it shows that there are a handful of the time in the year that data center is crossing that 90 megawatt of threshold that we have set for interconnection. So actually, during those time, it will be good for the batteries to discharge and make sure that the data center output doesn't exceed that 90 megawatt threshold. So we loaded the data center profile. And the second thing we have to load in this case is the PV profile. So we also loaded that PV profile. If you click the drop down, you should see a data center example PV profile. Select that one. Once you select that, if you have auto update on, this figure should automatically get updated, and you should see that the PV coming is in the negative axis. So here, positive means from a battery perspective, discharge, and then from a load perspective, positive means load, and negative means generation. So here, the solar comes in as a negative injections. So once you have your solar profile loaded in, as well as your data center profile loaded in, the black one that you see here is basically your net. So that's the net of your load and your solar. Then you go to the dispatch parameter. So this is where you basically set the logic that when the battery should react. So on the discharge side, we set a logic that the net of solar and the load, data center load, it should not cross our discharge, the interconnection limits of 90 megawatt. So we set the discharge threshold to be 90 megawatt. So what does that mean? So what that means is that whenever that net demand is crossing the interconnection limit of 90 megawatt, the battery is going to be discharging to provide for that energy. And basically overall plant production or consumption is not going to go above 90 megawatt. And then on the charge side, we also have to make sure that charging the battery does not create a new peak, right? So what we do is here we set the charging threshold to be around 60 megawatt. So once we do that, what you can see here on the curve, there is a blue line, that's the discharge threshold at 90 megawatt. And then there is a green line, that is the threshold at 60 megawatt. So basically, whenever the net demand is going to fall below that 60 megawatt, that's when the battery is going to start to charge. That means the battery has some headroom before it reaches 90 megawatt, and your battery is not going to cause a different peak. So that's why we added the charge threshold to be 60 and the discharge threshold to be 90. So once that is done, then you go to the global input parameter, and then you utilize these two features. So first feature we are utilizing is we're also trying to apply a hard limit on the charge and discharge limit, because on the discharge side, we want it to be 100 megawatt equal to the data center load, because if there are outages and all, the battery should be able to provide the data center by its own. On the charge side, we do not want the battery to create additional peaks just because it was trying to charge at a higher power. So we applied a 25 megawatt of charge limit so that in that way, your battery charging rate is slowed down, and you're making sure the battery is not causing additional peak, because one of the nature of this data center load profile, you'll see that is very like flat, right? It's more or less flat. It's kind of up there. So there is not a lot of valley where your battery has a lot of headroom to charge. So you have to kind of limit how much the battery can, like whatever power level the battery can charge at. Once that's done, then the next thing is that you have to apply that equalization, and that's important because a lot of times if you are just charging based on this profile, some days you can see there is just not enough energy available from the solar to charge your battery for the discharge. So to counteract that, you add this energy equalization feature. So you're basically setting a time window between 7 a.m. to 5 p.m. That basically tells that in that 7 a.m. to 5 p.m., whatever amount of energy you needed to discharge in that day, you're making sure that you're putting enough amount of charge energy back into the battery, right? Because otherwise, if your battery doesn't have energy, it's not going to be able to give any energy. So you're setting a time window, and you're setting a discharge ratio, and that's basically controlling how much energy you're putting in. So if from your solar, if you're not putting in enough, then during this time period, this is going to take help from the grid and put some additional energy so that your battery has enough energy. Once that's done, you go ahead and run it and then look at the generate report. And one feature I'll show you as well as the report gets generated is that now, even without running it, if you click update button here under full profile, you will be able to see the profile that got generated. So this basically telling that this is the charging discharging pattern that got generated. So during the summer months and all, battery charged more, discharged more. In the winter month, it had to do less. And now if you go back to the report here.
And also, Jakir, something to note as well, users can also switch to the battery system modeler. So if you go to the battery system modeler right now, right, under interval data, you'll see here, it's been automatically selected under the time series when you ran the battery profile creator. And now you can see the POI profile, but in addition to what the VPC is showing, you can see the 24-hour profile, the power histogram, right? So it gives you a picture of, every day over a 24-hour period, what exactly is happening, when this battery system will be charging, when it will be discharging. The power histogram tells you, all right, the distribution of power set points on this planned battery system. And the energy histogram tells you the same for energy throughput as well.
Yep, good point. And then we're going to do the same here in the report, because report also gives us something similar information. So it first goes with application specific. So it is kind of showing you that you are charging mostly during the daytime from the solar, and then you are discharging it back to the grid when there is a need. It gives you that 8760 profile for your batteries. And then it also showing you different analytics around what's going to be your net demand after adding the solar, adding the storage. So I'm going to skip this and jump to the main section here, which is the real question we have up until now is that we don't know that how big of a battery you're going to need. And this histogram is going to help us answer that. So what this histogram is telling us that on the secondary axis, this orange one is a cumulative distributed function. So if we pick a 17.5 megawatt battery, it's basically going to be able to meet the discharge requirement almost 99% of the time. If you see it where it intercepts the y-axis. And to get to, so basically if we go at a 20 megawatt battery, we will be able to meet both charge and discharge side 100% of the time. So we can select a 20 megawatt battery from this, because we are trying to make sure we never cross that 90 megawatt threshold. Right? That's a hard limit from the interconnection perspective. So we are going for 100%. We want to make sure there is not a single point that goes up beyond that 90. So based on this, we decided, yeah, we need a 20 megawatt battery. And then we come to the energy histogram. This is telling us a similar story, that on the discharge side, we need maybe 55 megawatt hour. On the charge side, we need like up to 75, 80 megawatt hour. So if we go with an 80 megawatt hour, we will be able to meet the energy requirements fully. So what we take out from this module here is that, yes, we're going to go with a 20 megawatt, 80 megawatt hour battery for this application. And then this is going to be the use case profile for that battery. With that, then we come to this battery system modeler module. So you will see under general, as you switch, it's a 20 megawatt, 80 megawatt hour battery. We are not doing any augmentation at this for this example, just set it to user defined, set the usual parameters as we have discussed before. Interval data, so the power, this profile got automatically populated when we ran this other module, the battery profile creator, and then it gets loaded. Under equipment, this one we're using a 14 ampere hour model. So previous one we used 80, first one we used 306, now we're using 314, right? So we're using different battery models to see how the performance and things back. Inverters still kept the SMA1, and the enclosure still kept the same liquid cooled enclosure. Then you come here, you basically at this point click auto size, and this is gonna auto size the project. So primarily, if you just do general interval and equipment, if you're not doing augmentation, those are the only 3 information you need. And then as soon as you input that, auto size becomes sustainable. You click that, it's gonna auto size the project for you.
So while that is running, something that's probably worth noting. So if we go back real quick to the energy histogram, Jakir, right? One of the uses of this energy histogram is to kind of properly size your system. So in some scenarios, you would need to just double, the energy capacity of your battery system to get that last 3% or 3 percentile of days on either discharge or charge, right? So it helps you identify when you start to get diminishing returns. Like for example, here on the charge side, here, if you look at the orange cumulative percentage, right? What seems to be going from, if you just ignore from 40 megawatt hours onwards, but if you just look at, from 30 megawatt hours to 40 megawatt hours, you're not really gaining much by, going from 30 megawatt hours to 40 megawatt hours, right? So it helps, the percentage of the days with certain charge and discharge throughput, so you can kind of size your battery system based on a capacity that is not getting diminishing returns. All right, back to you, Jakir.
Yeah, and then when the augmentation of the auto size finishes, it's basically showing you that you need an install capacity of 112 megawatt hour to get 80 megawatt hour throughout the project at POI. Okay. And you also need your inverter is a little bit oversized. We talked about doing 20 megawatt, but we need 23.8 because of the losses and other factors that we talked about before. So once that's done, you basically at that point just go ahead and run it. And then do generate report. So a couple of things are important here. So one thing we want to make sure that the system we design is able to meet the discharge power and energy requirement very well, because if we're not meeting our discharge commitment, then there is a chance that the overall planned output is going to exceed 90 megawatt. So in this case, you can clearly see that on the discharge side, we are like 99.7%, and that's the goal, is to meet the discharge throughput. The throughput is a bit less because what the profile is trying to do is put all the solar energy into the battery. So the battery is sized for discharge requirements. So you sometimes, like in certain conditions, you are not able to put all those solar energy back into the battery because the battery is not big enough. And it doesn't need to be, because you only want to charge it enough so that you can meet your discharge requirement. All right, so with that, then you go ahead with the usual discussion, your RTEs, your losses. Another important thing for you to check is your overall POI capacity, which was 80 megawatt hour. This one, we didn't do any augmentation. So the initial system is completely overbuilt for 20 years. So we did that one. And then eventually you get the cost of your system along with all the operational cost that we talked about. This one didn't have revenue. If you want, you could add revenue if you had a certain kind of contract structure, but we did this example without the revenue. So now after doing all these, the main thing we're trying to look for, because our goal was to ensure that our overall plan output doesn't exceed that 90 megawatt threshold, right? So after you ran this module, the Storlytics output is that if you go to the generate CSV, it gives you exactly what the battery is going to be charging, discharging at the POI, right, at the battery point of interconnect. So if you go to the Excel, the output here, so if you output DSM, this is the one that just got created. There are quite a few different files that get created. There are some daily data analytics, annual analytics, and financial analytics. The one that we're looking for is this one, time step. So that's like every time step, what happened in your system from all the way to point of interconnect to the battery terminal. losses and active power, reactive power flows, everything is laid out here. So here, this is the column you're looking for. So this is what actually your battery is going to be doing. So if you take this one, P grid actual, and then combine that with your data center load and your solar production, then you'll be able to get your net production. And that's what I have here. So here what it shows that the red one is the data center load, which was some places at times you can see over the years was going above 90 megawatt. But then the green one here is the data center net load after adding the storage and solar to on top of it, right? So we can see that the green one never exceeds that 90 megawatt threshold. So what it basically tells us that with the help of solar and storage, we were able to add some flexibility and bring the interconnection limit from 100 megawatt to 90 megawatt. So in that way, now this data center is going to be able to connect with the utility without much of an upgrade requirements or delays. So I'm going to stop here. Obviously, there are a lot of other variations you can do. You might want to go back and add some diesel as well. It really depends on the shape of your data center load, as well as your solar, how big it is and how big of a footprint you have. But then if you want to add some other generating resource, you can come to the microgrid demand app through the wind profile. It says wind, doesn't have to be wind. So if you have a natural gas generator that is going to be running at a base load, you can input that through the profile here. So there are quite a few different resource mix you can do to determine what size of batteries you're going to really be needed to basically add data center flexibility. So that I'm going to stop here. That's what I had for this example. Let's see if you have any questions.
Yeah, so in this example, the solar isn't supplying 100% of the data center requirement, right?
Correct.
The data center is getting probably most of its energy from the grid.
I mean, so you can see the data center is like 100 megawatt, hovering around 75 or so. Solar is peak at 75. And especially during this winter months and all, the solar is just not producing enough. So that, yes, it's taking the data center is taking help from the grid.
Yep.
And I get your, it's a really good question because you want to make sure that you don't need to get power from the grid at the same time the load from the data center is at a maximum, because that just defeats the whole purpose, right? So that's why in the battery profile creator under global inputs, if you go to the energy equalizer, you try to spread out that duration, the difference between start time and end time, as much as possible, because that way you're making sure that the power at which you're charging from the grid is as small as possible. Because when you have long time to charge to get to a certain state of charge target, the power level you're going to be at is going to be minimal. So to check that, you can look at the CSV and make sure that you're not charging at the time where there's peak load from the data center.
Yeah, I guess, and my point is that in some cases that we've been considering, we want to provide as much solar to the data center as possible. And, think of it as how much decarbonized power do they have versus generic grid power.
Yeah.
And in that case, you'd have to upsize your solar by a factor of 3 or something, depending on your local capacity factor and resource.
Mm-hmm.
But
Like
that'd be a very different case to try to manage.
Yep, absolutely. And just to clarify, you mean to be fully fed from solar energy, right?
Well, you may not get there, practically speaking, but maybe you get to 90%, maybe you get to 70%,
Yep.
But,
Yep. The amount of oversizing, like solar capacity to load capacity in cases like that is really, really high. I know that because we just ran a case like that a couple of weeks ago with one of our consulting partners, and to be 100% fed from a solar resource, the ratio is just very, very high.
And it's challenging, right? You can do the solar at a certain cost, and then if you want the battery to smooth it all out, to reshape it, then you find that you're increasing your cost significantly. Maybe you're adding 50% to what would have been just a solar cost.
Yep, makes sense.
Fine.
Awesome.
Question is whether people want to pay for that or not.
Yeah, that's always the question.
Thank you.
All
All
right.
right, thanks, Al. All right, any other questions? Let's see, I think we have a question from Thomas. Is a data center model assuming perfect foresight of PV generation?
Yeah, right now, yes, we are inputting the PV in output. So yeah, we're assuming that we know what the PV is going to produce.
Right, and it could be either, obviously historical PV data, or, in most cases, it's just PV syst profiles, 8760s that are used as inputs. But yep, definitely assuming perfect foresight. Now, that opens the question of, all right, how conservative or optimistic do we want to be? And, we highly advise people to kind of apply their own kind of engineering practices. But like something you could do is in the PV profile multiplier that you see there in the second line under general settings, you could kind of update that to be, 90%, for example, if you want it to be a little bit conservative on how much the solar is going to produce. So that could be varied easily. All right. Any other questions before we move on? All right. Not hearing any
I'll
questions.
give it back to you.
All right. So thanks, Jakir, for that. What I'll do here is we'll kind of start on this fourth and final example. So designing a battery system that will be AC coupled to a solar system. So here's the scenario description. An existing solar PV facility, let's call it San Diego Solar, is constantly curtailing or clipping energy during the spring due to interconnection limit of 75 megawatts. We seek to design a BESS system to do the following. Basically charge from solar when solar power is exceeding the interconnection limit of 75 megawatt. And then when solar is not producing, overcast days, we want to be performing energy arbitrage to benefit from, different rates during peak hours and non-peak hours. All right, go ahead and switch screens here, or I can actually just use this one. So here we'll do a new project, okay? And then we'll just go to the battery profile creator. And from there, we'll turn on clipped energy storage. And let me just get the slides here, the other screen. All right, since we selected the clipped energy storage app, we'll go to the app tab here and then select the PV profile of that PV facility. So San Diego Solar. So as soon as we select that, kind of pops up here. And then, we input the charge threshold. So in our case, the interconnection limit is 75 megawatts. So basically any power greater than 75 megawatts, we want to charge to make sure we don't exceed the interconnection limit. And for the charge power ratio, we want to be at 100%. So 100% of the power that is greater than 75 megawatts will want to charge that. All right, now let's go to the global user inputs, or global inputs rather. And we'll use the equalize daily discharge and charge energy function. And what this function does is on a daily basis, right, it looks at the energy that was charged from the solar in this app, okay? And it just counteracts that amount of energy in the time you specify. So for us, we're just going to specify that, all right, any energy you collect from the solar facility, right, discharge that between 5 p.m. to 11 p.m. Okay. And then for the discharge charge ratio, we'll just set that to 85%. Now this, ratio just mostly corresponds to what you expect your round trip efficiency to be. Obviously, any energy source system is not 100% efficient, so you should expect to discharge less than what you charge. So here we're setting it to 85%. Right, and then after that, we come here. Here we specify the number of days, so we're going to do 365 days. And then we'll click run. One more input profile does not match the base. Oh, this is set to 15 minutes, while I think the input profile is 1 hour. Why I got that error. Let's click run. Right. So completed successfully. So then I can go to the full profile. I can click update here, right, and see how the battery system is dispatching, right? So charging from solar and then discharging later. And one thing else that's very notable is that there's just a lot of days that this battery system will not be doing anything. It will just be kind of sitting there. So per the scenario description here, we had a secondary application, right? We wanted to charge from the grid when there's no PV output, right? So we can kind of make a little bit more money from this battery system, right? Get some more value out of it. So then how do we do that? How do we specify that if there isn't any solar output, let's charge from the grid? So the way we do that is adding another application here, schedule. And something that I kind of did not fully clarify is that we're running in priority mode. So when we add different apps here, they just get added to this priority list, and I can kind of shift these different applications so that I prioritize versus the other. So here, my top priority is clipped energy storage because I want, to prioritize that. And second priority here is schedule, right? Then I can turn off these others that are not needed. So that basically means when power is needed to charge from solar, it'll prioritize that over energy arbitrage, which is the schedule app here. So here we'll set the charge schedule. But before we do that, let's look at the power of the system we designed, right? So if we go to interval data here and select, oh, I think I didn't have the this on. Let me turn this off. Okay, so now it loaded the profile here, and it just called it unnamed project because I didn't specify a project name. And now I can see kind of the distribution of power set points and energy set points here, right, in the 24-hour profile, when the system is going to be charging, when it's going to be discharging. And one thing I can glean from the energy histogram is that about 58% of the days, there is neither charge throughput or discharge throughput. That's also very clear here, right? So that's like about 58% of the days the battery is just sitting there. But additionally, from these plots, I can specify what's going to be the power capacity of my system, right? So here, since the primary use case of this BESS is to charge from solar to kind of make use of that energy, I want to focus on the power histogram here and specifically on the charge side. So here I can see if I'm at 20 megawatts, I'm going to be covering all the charge power set points. And then if I go to the energy histogram, again, focusing on the charge side, I see that if I'm at 80 megawatt hours, I'm covering about 96%. If you look at the bottom right there, I'm covering 96% of the days. So it really doesn't make sense to size my system based on 140 megawatt hours, right? Just for an additional 4% of the days to capture those fully, right? So then now we know that, okay, we should probably size this system to be 20 megawatts, 80 megawatt hours, okay? So then back here in the battery profile creator, as we're kind of specifying the schedule, right, we'll specify it with that in mind, that this is going to be a 20 megawatt, 80 megawatt hour battery system. So then here we'll just specify that we want to charge. And by the way, this is all written in the slides that should have been communicated to everyone, if anyone kind of is lagging. So here we specify that we want to charge at 20 megawatts, and the start time, we'll just do 8 a.m. to 2 p.m. Okay, and here it gives you the option to select the months, but I just want it for all the months, and I'll click add. So basically now I'm charging at 20 megawatts for 4 hours. Okay, so now we'll run that again. And by the way, I won't change the energy equalizer because that doesn't need to be changed here. Then click run again. Back to the battery system modeler. We'll see, starting with the energy histogram, a better distribution of throughput, right? So at the very least, you're charging from the grid. There's no kind of that delta we had here, it's no longer there, so you have a better utilization of this BESS. And kind of make it more visible here, show you kind of the comparison here from the slides. So this is what we had originally, was just PV clipped energy capture, and this is what we now have, adding energy arbitrage to it. Okay. And also you'll notice that the 24-hour profile makes much more sense over the original case, right? So in the beginning, with just PV, you had a lot of months where the battery's not doing anything, but here, even in December, right, where the battery wasn't doing anything, now you're doing energy arbitrage. The whole point is to just make sure that you're accounting for all the applications that either are planned to be executed or may be executed, to avoid undersizing your battery system. Okay, so now here I can come here to get into like the design portion of the BESS. I can specify that, okay, this BESS needs to be 20 megawatts, 80 megawatt hours, okay, with a project life of 20 years. And we'll keep the auxiliary source from the POI, and the interconnection, we'll keep it D-tied, because this is a really important point. If we look at kind of the scenario description, the battery system is going to be charging from the solar. So we want our point of interconnection to effectively be here, right? And that's what's coming out of the battery profile creator. Right. So then I think this is a better diagram. So this is the point of application of the point of interconnect. That's why here, even though the system is transmission tied, but here we're specifying it as D-tied, because that's where we want to apply our point of interconnection, right? It's being applied right here. Then we'll use financial results, battery degradation, set it to 100%, or the initial state of health, set to 100%, and deduce enclosure temperature auxiliary load. Then we'll get into turbo data. It's already pre-selected to be time series. For the TMY3 profile, I think this was San Diego. So we'll select that file here. And then under equipment, going off of memory here, let's see what we had in this example. Right. So we had generic LFP 314. For the inverter model, we're using SMA Sunny Central 2750. And then for the enclosure, we'll use air-cooled steel enclosure. And now as soon as I input that enclosure, you see the auto size project button has come on. So then I can click that, then click OK. And then it'll automatically start sizing my project. Now let's look at the message here. Auto size project could not find an appropriate value for number of modules per rack. Try changing the battery or inverter models to allow better compatibility. What is that telling you? The reason that message is coming up is the battery model is incompatible with the inverter model, right? And some reason that may be happening is because the module voltage is just too high to the point where adding incremental modules on top of each other to form a rack just creates a voltage that is incompatible with the selected inverter. So what we can do here is switch to maybe a 306 amp hour. I think this one has a different voltage level. And then let's try auto sizing again. Okay, looks like it's working. All right, so while this system is auto sizing, any questions?
Yeah, Jermaine has.
Sure.
We're selecting the arbitrage, but we haven't examined or have in front of us a price signal, right?
Correct. And the assumption is I think it's maybe there in the scenario description, but the assumption is that there is an incentive to perform arbitrage, right? Different price signals or different prices for different times of days. But yeah, that's just one example. So yes, we are assuming that the rates in the evening are higher than the rates in the daytime in this example.
Yeah, but I mean, maybe it's something for future development, but my concern would be if that revenue doesn't exceed your losses through efficiency, you're actually hurting instead of helping, right? There's got to be enough delta in that price signal to pay for the losses.
Yep. And you should be able to deduce that in this version. So under the financial model here, you can select, I think if you specify merchant market, help me out here, Jakir.
Go to the financial model.
Yep. Oh,
Open
here.
it up. Yeah. Go under merchant revenue, merchant market. So this is where you can bring in your own pricing data, right? So basically, if you have a set of data where peak hours has more price and that's where you're discharging, and then when you're charging when off peak hours, then this is going to couple that with your simulation output, and it's going to give you a revenue projection. And you can then take that and see if that lucrative enough for you or not. Yep.
Okay.
So you can basically do a simulation with arbitrage and without arbitrage, and then both look at the total revenue and also cost of ownership. Because when you do arbitrage, that's going to obviously cause degradation. You're going to need more battery capacity. So then you can see if the cost of the additional battery capacity is worth the additional revenue over project life.
Yep. Good. Thank you.
Yep. Sure. Right. Okay. Now the auto size has completed. If we go under system specs here, see the number of modules, number of racks, and number of inverters has been populated here, and losses as well, as we discussed before. Operation as well. These have been filled out. I'm just going to kind of load the example file here just to make sure not missing anything. There we go. And also for those of you following along, you should have, when you go to open here, you should have this file, webinar_solar plus storage. So you can just load that. It'll populate all the information I just populated here. All right, so now under financial tab, we selected generic lithium LFP. This one doesn't have the ITC in it. So we'll deduce cost and then selected basically all the cost components under here. Then click run. Have the report here. It's done. So generate report, right? And now we have the report here. So some things we just need to check on in this report. Let's see here. Right, so the first thing is the achievement. See, we're at 95%, and that kind of aligns with our design, right? Our charge throughput is at 95% achievement, because remember, when we were kind of looking at the energy histogram, we saw that, okay, we don't really need to go to 140 or 150 megawatt hours. We can cover about 96 or 95% by just being at 80. So that totally aligns with what we were shooting for here. And then the other thing we want to look at is the state of charge, right? Now, why is this happening? And just to explain what's happening here. So on the x-axis here, these are the days in the simulation. On the y-axis, this is the state of charge. So what this is telling you is that day over day, your state of charge is going up. And what that means is on a daily basis, you're not correcting or steering your state of charge to keep it within a normal band. And this is not how battery systems are operated. In operations, what operators will do is on a daily basis, they will take some time out to basically charge or discharge the system to get it to a state of charge where it's ready for its next operation. So in our example here, what your battery system will need to do is it'll need to be at a minimal state of charge at the beginning of the day, because it's expected to charge in the daytime, right? So it's probably a good idea to use that time, maybe 1 a.m. to 6 a.m. or 7 a.m. to get the state of charge down to a point where it's ready to charge from solar or from the grid, in the morning. So why not just ignore this and then just use the financial results here, right? The reason we would not want to ignore something like this is because for most lithium systems, being at a high state of charge for a long time results in more degradation than if you're kind of at the lower or a mid state of charge range. So the whole purpose of why we're doing this is we want to be as accurate as possible. We want to mimic what is actually going to happen in operation. So basically we can go back here into operation and turn on daily state of charge steer. And the way we can set it up is we'll set up to a state of charge target of 15% and at 20 megawatts between 1 a.m. to 5 a.m. So that basically means in this time period where this BESS is not really doing much, right? It'll discharge to get the state of charge down to 15% here per the SOC target. So it's ready to kind of charge from the solar and then discharge that energy later. Okay. So right now with the current design, the size of the battery system we need is about 148 megawatt hours, right? So let's see, once we auto size again, this time with daily state of charge on, difference we're going to have. So we would expect the needed battery capacity to go down because now we would be like the state of charge would be at a kind of a lower band, which is less impactful than constantly being at a higher band. But let's see what happens. So here in this case, we degraded from 100% down to 65.6% at year 20 rather. Well, let's see here. All right, it's done. So if we look at the messages in the status log, we can see that the number of battery motors per rack was automatically changed from 4 to 4, so no change there. And the number of inverters was 20 and is still 20. And that makes sense because we didn't change any power requirement. But the number of battery racks per inverter changed from 40 to 38. Okay. And that's mainly because now we have less degradation, so we need less battery capacity up front for this project. Right. So now let's run this and we can kind of look at both reports and see kind of the difference. So generate report. All right, so let's put this on the left and this one on the right. So how can I minimize this? All right. The right is without state of charge steering. The one on the left is with state of charge steering. So let's look at the degradation table here. So without state of charge steering, we degraded down to 65.6%. With state of charge steering, we degraded down to 71.3%, which means we needed less capacity up front with state of charge steering. Okay. Now, what kind of cost impact does that have? Let's go here to the net present value charts. All right, I think we need to look at the table for this one. So product cost here, we're at 39.6 million. Here, we're at 37.8. So little over kind of 1 million in savings or so. That's just from correctly assuming how the battery system is going to be dispatched. Now, let's look at the actual state of charge chart that really started all this. So here's without state of charge steering. So you can see here day over day, your state of charge band is shooting up, right? But here, you're kind of more consistent. You're hovering around the bottom kind of state of charge band on a daily basis, correcting to 15%, which kind of is more in line with normal practices for operating BESS systems. Okay, so that was a lot, and there's a couple of other charts here. Probably would have been easier for me to show. But yeah, any questions at this point? We're 20 minutes over, but we wanted to kind of fit in this example because we think a lot of people have different scenarios with hybrid solar plus storage projects. All right, Q&A here. What was the motivation for choosing 1 a.m. to 5 a.m. for the discharge to a lower set point? So Michael is referring to basically the state of charge steering here. So here we set it to 15% from 1 a.m. to 5 a.m. So why did we select this time frame? The reason I selected this time frame is because when I looked at the 24-hour profile here, I noticed that there's really not much happening in that time of day. So I didn't want to interfere with other kind of BESS operation. And additionally, this is, talking with a lot of operators, this is what's most common. That night period is when operators is most commonly used for operators to kind of correct state of charge. But there is no wrong answer here. The only wrong answer is not assuming the system will be dispatched as it most likely will, right? So you want to be as close as possible to how you expect the system to be dispatched. If that means updating to maybe steering state of charge here at this point, that's fine as well. Right, from Oscar in the Q&A, is PV profile provided for the lifetime of the project? Is then BESS system considering the PV degradation over project lifetime? So to answer that question, the PV profile here can be whatever you want it to be, but it is a 1 year profile, 365 days. So you can update the CSV to maybe base your system design on maybe a degraded system. You could use the input, the PV multiplier here. So you could kind of reduce that to assume your PV panels have degraded. But yeah, it's 1 year of data. Okay, I think that's it. Oh, there's another question here. Priscilla. EMS operators typically operating projects with something like SOC steering in practice? Yes. Yeah. Looking at a lot of power plant controllers, there are the exact same functionalities there in EMSs where you set, the operator does not set or sets directly a state of charge target and a time range and a power set point, and doesn't really, like, the only control objective is to reach that state of charge target. So it doesn't fill this full time. What this is saying is from 1 a.m. to 5 a.m., through controlling the power being dispatched at the point of interconnect, reach a state of charge target of 15% using a 20 megawatt set point. So it is primarily based on, like, the PI controller is based on the state of charge target, not a power set point. All right. Any other questions? I think that's all the questions in the Q&A. That's it. If there are no other questions, we greatly appreciate everyone's attention. As mentioned, this webinar has been recorded. We'll share the recording with everyone. If you haven't already received the slides, you should be receiving that soon. And as always, if you have any questions, comments, please don't hesitate to reach out. Thank you all for your attention. All right, bye. Thanks.
Thank you.